Hi everybody, this is Miss PG again from WCA Physics class. We are looking at Unit 5 and Lesson 2, Forms of Energy. So this is Semester A, and we're going to kind of go through this one. It's going to take a little bit longer, I think, simply because there's math, and I know you guys always want me to go through the math just a little bit more detailed to give you kind of practice and stuff with how to do it. So our keywords here are energy, gravitational potential energy, kinetic energy, law of conservation of energy, potential energy, and velocity. So lots of energy happening here. But that's okay. We're going to be learning all about energy in this unit. So first talking about the many different forms of energy. Energy is defined as the ability to do work. So you kind of need to know what work is first. And it kind of goes out of order here a little bit, but whenever you move something, apply a force to move something over a distance, you are doing work on that item. So if I take this and I pick it up, I'm moving this little box over a distance. I'm applying a force to move it. So I'm doing work on it. I have the ability to do work on it, so I'm using energy. It is in motion at this time. While it's moving, that's considered kinetic energy because kinetic energy is due to motion. Another way of thinking about it is if I were to drop this on my hand, I'm going to open my hand up. It applies a force when it hits my hand. It does work on my hand. It's not a very big thing, so it's not applying a lot of kinetic energy, but it can do work on my hand. If it was very large, my hand would move. So the larger this would be, my hand would actually have to move a little bit to kind of like bring it in and hold it, right? So it's going to do more work on my hand. As is, my hand doesn't move very much at all because it's very, very little amount of energy, kinetic energy. The faster it's moving, the more work it can do on my hand, and the more mass it has, the more work it can do on my hand. So if it was somebody threw it really, really hard, I'd have to move my hand kind of, or if it was very, very massive, very heavy, I would also have to move my hand a lot. So the amount of work it can do on my hand depends upon the mass and depends upon the velocity of that item, right? That's kinetic energy. It's moving. If I hold it up here to drop it in my hand, I'm not actually moving it right now, so it doesn't have kinetic energy, but it has the potential to do work. If I dropped it, it would do work on my hand. If I held it up here, it's going to fall farther, so it's going to have a higher velocity when it hits my hand. Therefore, it can actually do more work on my hand from this height than it could from this height, right? So this is going to go pretty slow when it hits my hand. Up here, it goes a lot faster, hits my hand a lot harder, therefore it can do more work on my hand. So the amount of potential energy that it has, it's not having energy yet, but it has the potential to do work, is directly dependent upon how high I hold this container, the height of the container. So we have our kinetic energy, and you can see that kinetic energy is equal to 1/2 times mv squared, where m represents the mass of the object and v represents the velocity. Like I said, if the container, this is actually a container of mints, and they're very delicious, but if it has more mass to it, it can do more work on my hand. So it's increasing kinetic energy. Or if it's going faster, if I threw it instead of just dropping it, it's going to have more velocity, therefore it can do more work on my hand too. So those two factors, mass and velocity, affect the amount of kinetic energy because when it falls, it's hitting my hand, it's moving at that point, and that is what kinetic energy is. Potential energy is stored energy, and it's directly dependent upon the height of the object above the surface of the Earth. Gravitational potential energy, abbreviated GPE, we're distinguishing it from other types of potential energy because there's not just gravitational potential energy. There's different kinds, and I don't have a rubber band in here, but say you had an elastic band, which I don't think I have, guys. I'm going to look and see if I have it in my drawer. Yeah, I do, right here. So here's a rubber band. This has elastic potential energy. It's different, right? If I want to snap this on my hand, it's going to hurt. So I'm sacrificing myself for science right now, but I stretch it a little bit and snap it, it doesn't really feel like much of anything. So it doesn't really hurt or do much work on my hand. But if I pull it really far and stretch it more, ow, that kind of stung. It's going to do more work on my hand in that situation. So that's called elastic potential energy. Elastic potential energy can be converted to kinetic potential energy or kinetic energy too. Once I let go of it, it's moving and therefore it has kinetic energy and not potential energy anymore. We're specifically looking at gravitational. Gravitational is dependent upon how high I hold this. The higher I hold it, the farther it can drop, the more velocity can build up. Therefore, the more kinetic energy it has when it hits. Therefore, the higher it is, the more potential energy it has. So GPE, gravitational potential energy, is equal to mass times little g, which is the acceleration due to gravity, times h, which is height. Now, we didn't talk about mass in regards to gravitational potential energy. If I hold this up higher, it can do more work on my hand, but also if it's heavier, it can too. If I hold it at the same height, two objects at the same height, and one is heavier than the other, the one that's heavier is going to do more work when it hits the ground. Think about dropping a softball versus a shot put. You know, the shot put is going to do a lot more work on the ground than the softball will, even though they're approximately the same size. So again, mass is measured in kilograms, height is measured in meters, and little g is 9.8 meters per second squared. You're going to use that a lot this semester. This is the gravitational acceleration due to gravity on Earth. So the amount that Earth's gravity causes you to speed up when you fall. That's what that means. So essentially, we're saying is that there is a conservation of energy law, that one type of energy is always going to convert to another. Energy can't be lost or gained, it only converts. So as I drop my mint container, it has lots of potential energy right here. As it's falling, it's losing potential energy because it's getting closer to the surface. It's, however, gaining kinetic energy because it's speeding up. So it will have lots of potential energy, but no kinetic energy when I'm holding it. When I drop it, it increases its potential energy because it keeps getting faster and faster until it hits. But it decreases, or it increases its kinetic energy, but it decreases its potential energy till it has zero potential energy once it is touching my hand. Okay, so one goes up and the other one goes down, but the sum of the two will always be equal. Let's do a little kind of pretend calculation to kind of show you that, right? All right, so what we're going to say is, let's say that is, I mean, it's really small. It's very lightweight, but we'll say just for argument's sake that it's a whole kilogram, which is 2.2 pounds. So it's seriously not that heavy. But I just want to make the math super easy. I'll make it half a kilogram just so that it's not like it's still a big exaggeration. There's no way there's a pound of mints there. I mean, that'd be great because I want more of them. But so let's say it's half a kilogram. Okay, so that is the mass times 9.8 meters per second squared. Okay, times half a meter ish. Okay, so that is the GPE, gravitational potential energy, because remember when it's up here, it's not moving. So the GPE is equal to this. But the kinetic energy is 0 because it's not moving. Our total energy is equal to the gravitational potential energy plus the kinetic energy. Okay, so let's figure out the math there. So I work old-fashioned. I have a calculator, a TI-30 X, my favorite calculator. I know some people use online calculators or you use your phone or whatever. I prefer to use an actual calculator. So I'm going to take 0.5 times 9.8 times 0.5, and I get 2.45. And let's look at this. So meters are going to cancel. And we've got kilograms. Oops, my bad. Meters do not cancel. They're both on top. I was screwed up there. So we end up with meters squared. Oh, take that back. Forgot my kilogram. So kilogram meter per second squared. And I'm just going to put times meters because this is going to make it a little easier. This is where units kind of get a little funky in physics. In physics, 1 kilogram meter per second squared is a Newton. That's what a Newton is. A Newton is a kilogram meter per second squared. So this here becomes Newton. We're just going to substitute Newton. And we have Newton meter. And another name for a Newton meter is a joule. So our answer actually is 2.45 joules. That's our final answer, which is the unit for energy. Okay? So our total energy is 2.45 plus 0, which is 2.45 joules. All right. So that's what the energy it has when it's up here, top of its head. So let's say I drop it and it falls and hits my hand and it's falling. Let's see, we need to use this equation one here, 1/2 mass times velocity squared. So I don't know how fast it's going to fall. I don't have any idea how fast it's going to fall. But I do know some other things. I know that when it hits my hand, it will have gained all of the potential energy will now have converted to kinetic energy. So right here, remember, it's stationary. So all potential, no kinetic. Right here, the very point that it hits my hand, it's all kinetic, no potential. So at the very bottom, it's going to be 100% kinetic energy. So I'm going to figure out how fast it's going here. Kinetic energy, I'm going to say, is going to be equal to 2.45 joules because it should be equal to the potential energy because that's what the law of conservation of energy tells us. So kinetic energy, 2.45 joules, equals 1/2. The mass of it was 1/2 of kilogram. And then times velocity squared, which we don't know what that is. But I'm going to solve for it because we can do that. That's what's cool. So I'm going to just isolate v squared here. So to do that, I'm going to multiply both sides by 2 because if I want to get rid of the 1/2, I'm going to multiply by the reciprocal, which means I'm multiplying by 2 on this side. That gets rid of my half. Okay. Multiply this side by 2. So 2.45 times 2 is 4.9. And then I also need to get rid of that 0.5 on the right side here. So I'm going to divide by 0.5 because if I want to get rid of something here, it's multiplied by v, so I'm going to divide it by 0.5 to get rid of it. So divide this side by 0.5 is 9.8. So I end up with 9.8. and it's joules divided by kilograms, which at this point we're going to pretend like we're going to ignore units for now, equals v squared. And then I got to get rid of that square, so I'm going to take the square root of both sides. The square root of 9.8 is 3.13. So it tells us that it's going 3.13 meters per second when it hits my hand. Okay. So that's kind of cool because you can figure out something you didn't know because of the law of conservation of energy. So you've kind of learned in this lesson here then what kinetic energy is, what potential energy is, what the law of conservation of energy is, and how you can use that to determine the velocity when it's at its lowest point. That's pretty neat. Or really at any point. I mean, it doesn't have to be at the lowest point. We could figure out its velocity at a different point there too. So that kind of walks us through like the main points of this lesson. They do talk a little bit about, roller coasters and how you can do the same kind of thing on a roller coaster. The idea is if you're at the top of the roller coaster, let's see if I can get a new page here. I'm going to move this right here. But if you're at the top of the roller coaster, the very top here at the very first spot, you have a maximum amount of kinetic energy or of potential energy. As you fall down, you go back up and you fall down, and you go back up and you fall down. Okay. So at any point along the track, your total energy is equal to potential energy plus kinetic energy. Any point. Doesn't matter where you are. There, could be there, could be here, could be at the top of this hill. Doesn't matter. It's always going to be PE plus KE. This point is unique though, because here, all of it is potential. Kinetic energy at this point is 0. So at the very first spot where you are in the roller coaster, the total energy and the potential energy are the same. And that's an important thing because it's going to tell me then how much my total energy is everywhere. So we'll always know the total energy because it will be equal to the potential energy at the top of where you began on the roller coaster. So to figure out energy anywhere, potential energy anywhere, you just have to know one or the other, right? So it kind of helps you to determine what your energy is at any point along the track. As long as you know the height, as long as you know what total energy is, if you know one or the other, you can figure this stuff out. Let's see here. So the example here is pretty much kind of the same type of an example that we did before. In this particular case, you're looking at a roller coaster that has a hill that's 99 meters tall, and you can figure out the gravitational potential energy of the roller coaster at the very top of the roller coaster because it's 99 meters. Again, you're going to use the mass of the roller coaster times 9.8 times 99 mgh to give you the gravitational potential energy of 4,365,900 joules. That's a lot of energy. That's the maximum amount of energy you're going to have at any time along this track because you can't create more energy out of nothing and you're not going to lose any energy really because your potential and your kinetic energy will always add up to this 4,365,900. So you can determine the potential energy at anywhere along the track because it's always going to be mgh. As you can see here, halfway down the track, the gravitational potential energy is 2,182,950 because we're using a different height. What that means, however, is that that's your potential energy, so your kinetic energy has to be the rest of it because the total energy was 4,365,900 and the total energy is the combination of potential plus kinetic. So if that's our potential, the kinetic is what's left over, which is 2 million, again, 2,182,950. When you're halfway down, you're kind of like half potential, half kinetic. So it's always going to be a sum of the two. Pretty simple, actually, once you get past just calculating what the potential energy is. It's always going to kind of work out that way. Then you can kind of do the same thing we did. Once you've got that, once you know how much kinetic energy there is, then you can work backwards and solve for velocity and figure out how fast the roller coaster is actually going, because you know its mass, you know the kinetic energy, you just need to know V. So you just need to solve this problem for velocity. It's exactly what we did with my breath mint example, but it's the same kind of situation, the same type of scenario that you will be expected to be able to solve. If you still need help on this, please reach out to me through webmail or give me a call here at school. Otherwise, I will see you in the next one.